right, welcome everyone to the ASA Committee on Law and Justice Statistics third webinar in our new series. We'll schedule approximately 5 to 6 30-minute webinars per year on data sets and statistical methods for the analysis of data in law and justice. Please stay in touch with the committee by filling out the Google form that I'll put in the chat here in a moment to get on our email listserv. Today, I'm pleased to introduce George Moeller for this session on statistical models of crime concentration. Please feel free to post your questions throughout the talk in the Q&A, and hopefully we'll have some time at the end for questions. And given that this is only a 30-minute webinar, I want to go ahead and get started, and please take it away whenever you're ready, George.
All right, thanks, Claire. So I decided to pick a topic that's sort of easy to state the problem, and I think it's kind of a good representation of quantitative problems in criminology and criminal justice, where there's kind of a need for collaboration with statisticians. So criminology doesn't always get the attention other fields get from statisticians, maybe, for example, in medicine, finance, climate change, but I think there is a lot of good areas to work in. And so this is just one example. I'm a professor of computer science at Boston College, also a committee member of the ASA Committee on Law and Justice Statistics. So crime concentration is kind of illustrated in this picture here. So these are some street segments in London, and I kind of put down some fake crime incidents on those streets. And what if you look at real crime data, what you'll see is that a large percentage of crime occurs in a small percentage of the city. So here, you have 3 incidents, maybe in a month, in one street segment in the middle, and there's this cluster of events in the middle of the figure. So there's a well-known criminologist named David Weisburd at George Mason University, and in his 2014 ASC Sutherland address, he came up with what's called the law of crime concentration. And roughly speaking, what he observed in a number of cities is about 50% of crime incidents occur in about 5% of cities. And this was pretty consistent across a number of cities he looked at. And if you're not unfamiliar, the Sutherland Address is the kind of most prestigious award at the ASC annual meeting. And this was also published in Criminology, which is the top journal in their field. And it's a very highly cited paper. So a lot of people have been interested in the law of crime concentration. Yeah, so it's, as somebody mentioned, it's like a specialized version of the 80-20 rule. I'm not going to spend too much time today on why crime concentrates. That's a whole nother talk, but you can imagine some of the answers. Some of them are geographical. So here on the left are burglaries in San Fernando Valley in California. And in the middle, you have housing density in that same area. So there's parks, and mountains where burglaries cannot occur. So that alone, will cause some clustering of events. And then you have areas where there's higher housing density and others. There's a number of other reasons why crime concentrates. I'll just give you one kind of interesting example, a second example. This was a paper in Science in 2008. Turns out, this was a randomized controlled experiment. Crime and disorder are more likely to occur in the alleyway on the right. So there, some neighborhoods have kind of signs of social disorder that lead crimes to cluster in those areas. This is sometimes called the broken windows hypothesis. So there's a variety of reasons why crime may concentrate in cities. What I want to focus on, like the first half of this talk, is not why crime concentrates, but actually how do you measure this crime concentration estimate that was in David Weisbird's 2014 address. So here's kind of the basic problem setup. You can do street segments. I kind of prefer to create a grid in the city, but you can do either one. And here we look at these 25 grid cells, and then we count the number of crimes in, say, the top two grid cells, and what we see versus the top one grid cell, we see 67% of crime is in 4% of the city, and then 100% of crime is in 8% of the city. And this is kind of the standard estimator used in criminological literature to quantify this crime concentration estimate. I would just call this like kind of the empirical crime concentration estimate. Now, a lot of, I'm not going to claim that the things I'll talk about are new. Some of this might be kind of reinvented in the criminological literature, but the long story short is, this crime concentration, estimate is actually a point on the Lorenz curve. So if we kind of order areas in the city by decreasing risk, and then we kind of plot the cumulative percentage of crime in those ranked spatial units, you get what's called the Lorenz curve. And then if you look at the area under that curve, that's how you determine the Gini index for inequality. And I guess the point of this kind of first half of the talk is these are actually statistics you need to estimate. And you need to, I would also argue you need to make your mathematical assumptions explicit. So why is this the case? Well, first of all, what are like the mathematical assumptions of this kind of standard estimator that people use? Well, basically, all you're doing is kind of taking these counts in each spatial unit, and you're using that to estimate the intensity of crime in each of those spatial units. And in this figure here, you can see why that would potentially be problematic, right? So you have lambda is estimated to be 2 and 1 in those spatial units. You have actually crimes in it, but everywhere else it's going to be estimated to be 0. And so in practice, when you use this estimate, it's severely biased. So in this plot, I'm plotting the empirical concentration as a function of the number of events used to compute that concentration for a fixed grid and a negative binomial distribution over counts in those events. And what you can see, is that for a low number of events, you have an extremely high empirical concentration where actually the true concentration is much lower, maybe around like between 0.2 and 0.25. And so this is also problematic, if you wanted to apply these concentration statistics across disaggregated crime types or comparing different cities over different years. And in the worst case, say this is just a Poisson process that's homogeneous across the city. If you just draw one event, you'll have 100% of crime in 4% of the city, even though the true crime concentration should be 4%. So the first person I saw in the criminological literature to kind of address this issue is a paper by Bernasco and Steenbeek in JQC. And their suggestion, if you're trying to estimate the Gini index, is to instead of kind of computing the area between the Lorenz curve and this line of equality, you actually define a new line of equality that adjusts for the fact that you might have more spatial units than you do crimes. And so they come up with this adjusted Gini index here to kind of adjust for this like overestimation of crime concentration when you're not in kind of the asymptotic regime. Unfortunately, this estimate is also highly biased kind of in the other direction for low crime counts. And then once you have the same number of crimes as the number of spatial units, then it matches up with the regular Gini index. So I think this is kind of where you need mathematical assumptions underlying this model of the intensity. So we had a paper in JQC in 2019 that suggested the following method to get a reduced bias estimate of crime concentration. So what you would do, you have your city and you have your crime counts, this histogram of counts across the city, fit a negative binomial to those counts, which tends to be fairly reasonable. And then you use the Poisson gamma representation for your negative binomial. And you take this gamma function and its parameters that fit those counts, and then you can integrate that gamma function's inverse cumulative distribution function to get the Lorenz curve. And similarly, you can use it also to compute the Gini index. And here's what you get when you do that. So you get what we empirically find to be an unbiased estimator. We don't have a proof for it, but it kind of fixes this issue for low and medium event counts with the kind of empirical estimate. There's been other models, suggested in the literature. Essentially, you're trying to model the intensity of crime across the city. There would be a number of different methods you could think of to do that. There's another JQC paper kind of around the same time of ours where they suggested using a Poisson mixture model. Which one should you use? Well, that depends on the data set. Here's an example where we used kind of 10 years or more of Chicago homicide data as ground truth, and then we kind of slowly, introduced events into the model and compared these two methods. For very low event counts, the Poisson gamma model does better, which makes sense because it only has two parameters. The Poisson mixture model is more of a semi-parametric method, so that tended to do better for larger event counts. Kind of more recently, this is a paper by Aaron Chalfin and collaborators. Maria Queller is another member of the ASA Law and Justice Statistics Committee. So I mentioned this paper. They recommend, instead of computing crime concentration, compute marginal crime concentration. So here you compare crime concentration to a homogeneous Poisson process. And in this one, it's flipped. So you're fixing the output of the Lorenz curve. So say at 50% of crime, and then you're estimating what percentage of crime captures, what percentage of the city captures 50% of crime. And so, you would want to not just know what this value is, but like how much more concentrated is it than random chance? And so this is what that estimator does. Kind of a similar idea, you don't want to just compute this statistic in isolation. It might be interesting to look at what it compares to. So there's another paper in Crime Science by John Eck and collaborators where they compared crime concentration to a number of other concentration statistics from other types of events. Kind of interesting, population, had a much higher concentration than crime concentration in their paper. So it's not just, crime isn't just directly proportional to population. There's something else going on. So I'm about how that was like the first half of this talk, just a very quick introduction to crime concentration. In the first half of the talk, we're kind of assuming that everything's stationary. So there is no time. We're just, estimating this density over space and then integrating it to calculate this crime concentration. But crime isn't stationary. And there's a lot of reasons why it might not be. Here's an example from a book from 1996 where a number of burglars that were interviewed. And this burglar is basically saying, I go back to the same house after I've committed a burglary, and I attempt to replicate that past success. So crime will cluster in time and space, as offenders replicate kind of past successes. This is sometimes called repeat victimization in criminology. And another, type of crime, for example, gun violence, you have contagion due to things like gang retaliation. So there's a number of papers that have modeled gang violence and shootings as a contagion process and estimated the reproduction number of shootings, which is, after an initial shooting, how many kind of follow-on shootings does that, is that expected to produce? So, in a JAMA paper in 2017, that reproduction number was estimated to be 0.63. For acoustic gunshot detections in Washington, D.C., that reproduction number was estimated to be lower, though I will say that there's kind of other incidents potentially in those acoustic gunshot detections that might be bringing that down. Nonetheless, this is something that also needs to be modeled. So now you can't model that as a stationary Poisson process. We have a paper from 2021 trying to estimate the changes in the reproduction number of gun violence during the COVID-19 pandemic. So here you have some baseline kind of rate that's like you could use a log Gaussian Cox process to do this, or some model that captures spatial heterogeneity in crime, but also things like day of the week and month and yearly effects. And then there's a second term on the right that models the contagiousness of events. So here you have a dynamic reproduction number, and then kind of a density in time that models the time between the serial interval between one event and like kind of an event that was caused by that previous event. And similarly, you have a spatial kernel that models the distribution in space of those contagion events. What we found was that in certain cities, the reproduction numbers seemed to go up, like in Los Angeles and Philadelphia. Other cities, that was not the case. But clearly, if the reproduction number of violence is changing, that kind of gives some indication that crime concentration is changing. So there may not be a law of crime concentration over time if certain types of crime events have non-stationary effects. And just to kind of give an illustration of this, right? Like here's a contagion process in space and time, and I'm at each time slice computing the Gini index, and it's a random variable that's changing over time. So probably research should more try to track the Gini index than assume it's fixed over time. Another reason crime is not necessarily stationary is there's actually a number of work related to hotspot policing and community-led interventions to try to reduce crime in what are called crime hotspots. So the law of crime concentration motivates things like hotspot policing and community-based interventions. One example is the Philadelphia Foot Patrol experiment, where the top 40 or so hotspots in Philadelphia were randomized into treatment and control. And then in the treatment hotspots, they had cadets do foot patrols for almost like 2/3 of the day, like 18 hours a day. And then in the control hotspots, there was no kind of cadet foot patrols. And they noted that there was a 20 to 30% reduction in crime in those treatment areas. But doesn't that, I would argue that if that's the case, then aren't you kind of disrupting the law of crime concentration? So it doesn't quite make sense that you can have both a law of crime concentration and effective hotspot policing experiments. So it seems like you would kind of have one or the other. And actually, if you kind of go back and look at this 2015 paper on the law of crime concentration, at least from what I could tell, one of these cities, if not more of them, had an intervention ongoing during the observation period where this crime concentration statistic was calculated. So in Cincinnati in 2009, there was a focused deterrence experiment and that seemed, at least in this Justice Quarterly paper, to reduce certain types of violent firearm incidents during that period. So the question is, in my mind, is there a law of crime concentration, even after you do these sorts of experiments? And if so, what does that kind of say about the effectiveness of these interventions? Um, I don't think there's a lot of empirical work to address this issue, but I will close this talk in the last kind of few minutes just mentioning a couple mathematical models that use simulation to at least explore this idea of how interventions might disrupt crime concentration. So this is a model I like from a PNAS paper by Martin Short and collaborators in 2010. So this is a reaction diffusion PDE. So burglars are randomly introduced into a city. They kind of move through Brownian motion, but they're biased towards areas that are more attractive to commit burglary. And then once they commit a crime, they're removed from that simulation. And then on the top PDE, you have housing attractiveness, where if a crime occurs at a house, that risk goes up. It becomes more attractive. And that attractiveness spreads to neighboring houses. And then in the absence of crime, decays back down to some baseline rate. So when you simulate there's an agent-based model that this PDE is a continuum limit of. When you simulate that, you get three types of behavior. You get no hotspots, stationary hotspots, and transient hotspots that kind of appear and then go away and move somewhere else. And in their PNAS paper, they actually do some experiments where they do hotspot policing. They suppress, say, all the hotspots on the top left, and then that leads to the figure in the top middle. But then if you kind of remove the suppression, what happens is those hotspots move to some new location, even if you keep the suppression there at those original spots. So this would be what's called like kind of crime displacement. However, under different parameter regimes, if you kind of suppress a hotspot in the middle on the bottom left, then that leads to no hotspot. So at least on this theoretical model, it actually depends on the parameters whether hotspot policing will disrupt the law of crime concentration, or in other parts of parameter space, you actually get no change to crime concentration. Now, in this model, you're kind of assuming that police decrease the crime rate. There's another paper in Significance in 2016 by Lum and Isaac, and this looks at crime. So burglary, for example, it has a 10% arrest rate or clearance rate. So most burglaries are reported to police, but police don't really kind of arrest people, and that it's kind of a process that's almost independent of police. But Lum and Isaac look at drug arrests in Oakland in a simulation-based model, and the idea here being is police have discretion, to make drug arrests, and potentially what you could have happen is, say you have drug arrest data, you define hotspots, you send police to those areas. Now, when they go back to those areas, they're going to make more arrests. You could actually have a feedback loop that increases the risk of more arrests in the future, and it actually would increase crime concentration rather than decrease it. So I think this is kind of my last slide of the talk here. I think it's kind of an open question whether these interventions reduce the crime concentration, increase it, don't change it at all. I think that's an understudied problem. So just my last slide is kind of the references that I drew upon for this kind of quick 25-minute talk that briefly introduces crime concentration. Thank you.
All right, thank you, George. I really appreciate this introduction. I want to encourage folks in the audience to put their questions in the Q&A feature of the webinar. In the meantime, there's a question in the chat from Ellen on the early models that you were talking about. They asked, are these estimates robust to the choice of grid?
Yeah, I think that's a great question. So the way I think about this in my mind, and I guess there's two ways to think about it. Is first, like I like to kind of think of things as continuous. So like I think that there's like this true continuous density of crime in space that you're trying to estimate. And so your choice of grid would affect, the accuracy of your estimate of that function. If it's too coarse, that's going to be problematic. But also, if it's too fine, you at least need some sort of regularization to estimate the smoothness of that function. Kind of the other answer to that question is maybe this is not a continuous process. So if we think about street segments or houses, for example, like there's a street network with nodes on that network being houses. And in that sense, you could formulate this as a discrete problem where that kind of issue goes away, but kind of the models that we're using take the first approach.
Yeah, so let's move in a different direction. Maria asked, where do you think that research is heading in policing with crime concentration or hotspots or other time geographic density estimations?
Yeah, I think I mean the place that I think is where research is needed is kind of around the last slide that I mentioned. So some of this is cyclical. So there's years where hotspot policing is popular. This tends to coincide where crime rates are higher in cities. And then, we had the murder of George Floyd at the, 5 or 6 years ago. And that, really, people really called into question, the role of policing. And you saw hotspot policing decline during that period. And so I think there's there's like a third variable that should be plotted here. And that's something like kind of trust in policing or grievances, towards policing. So really, I think hotspot policing is really kind of this relationship between the community who are potentially victims of crime and the police that can reduce victimization, but also policing also leads to unintended, traffic stops and arrests and can lead to excessive use of force. So there's some like kind of complicated objective function that has multiple, people that have different objectives in it. And it's very complicated, how you implement such a thing. So I think kind of studies are needed on how does policing negatively impact communities while potentially reducing crime? How effective is it at reducing crime? How does that interplay with crime concentration? And this is probably something that changes over time, so it needs to be dynamic. I don't know how you solve that problem, but that's something we've been thinking about.
Another question is maybe talking a little bit more about the incomplete ascertainment problem, incomplete ascertainment being a problem, even with the limited subset of crimes.
I'm sorry, what is that one?
I think, it was talking about what you were mentioning at the very end about I think it's talking about like whether we know about all of the different crimes that are happening and whether how much judgment police officers are using.
I see. Yeah. No, all of this kind of assumed, that these events are observed, that they're reported, that they're not falsely reported or so that is certainly an issue, and it gets better or worse depending on the crime type. So, probably, things like auto thefts they're probably, not underreported too often. If your car gets stolen, you're going to report it to police. And they're not like a discovery issue. Like, police don't go and discover, like auto thefts, and the absence of police leads to no auto thefts, where that is the case for drug crimes. Like for drug arrests, police have to go to that area, observe it, and then that will get reported. So I do think it depends on the type of incident you're looking at. And I will say that, for things where you are, worried about underreporting or overreporting, there are some interesting techniques to try to deal with that. Lum and Isaac have kind of a clever way to estimate drug use in Oakland based on survey data. There's other methodologies out there that try to estimate underreported crime. So there's a literature on that as well.
Yeah, that's what I was curious about too, if there are other data sets or other data types that could be used to sort of get a sense of the scope of that issue. Okay, I'm going to try to do one more question if you don't mind. We have a question. Do you think RCTs, randomized controlled trials, could be used in this useful in this area?
I actually think the first thing you could do is, if you had an RCT and you still had the data, you could one outcome you could measure is, did you impact the law of crime concentration in the city? So I think that would be kind of some low-hanging fruit to try to pick. I think going forward, I think there are a need for more field trials of interventions. I think there's a lot of kind of interest in kind of community-led interventions that where you bring in community partners to try to reduce harm in these hotspots that might complement kind of the roles that police have in a city. And so in those experiments, you could also imagine trying to look at potential impact on crime concentration.
Great. Well, thank you so much for this talk again. I want to thank everyone for coming. I also want to briefly mention our next webinar will be on December 5th at the same time, 1 p.m. Eastern, with Dr. Min Ji from the University of Maryland, and we hope to see you there. Please do sign up for our Google form if you'd like to stay in the loop on our email listserv. But otherwise, thanks again, George, and we hope to see you all at a future webinar.
Thanks for having me.